Welcome back to the Deep Dive, everyone. This is where we sift through a whole stack of info and pull out the gold for you. Today, we're getting into something that, okay, sounds pretty technical on the surface, the weldability of steels.
Yeah.
But, when we talk weldability, it's not just can you glue these bits of metal together. It's actually much deeper. It's about how easily can we make a joint that's, well, perfect, strong, safe, no hidden nasty surprises inside. Think bridges, buildings, even your car. It's all about stopping those tiny flaws that could cause big problems later on.
Exactly. And our mission today really is to give you a shortcut, a way to understand why some steels are just plain tricky to weld, and why certain steps, certain precautions are absolutely non-negotiable. We'll dig into the factors that play off each other, look at some common and sometimes quite sneaky weld defects, and crucially, how to avoid them. It often comes down to this really powerful idea. You usually only need to break one link in the chain of conditions to stop a failure.
Okay, that sets things up perfectly. Let's unpack this. So, practically speaking, what really makes the difference between a steel that's, say, easy to weld versus one that gives you, well, a massive headache?
That's a key question because it changes everything about how you approach the job. A steel with, let's say, good weldability, that's one where you can get a really solid sound weld pretty easily without needing tons of special tricks. It's forgiving. But a steel with poor weldability, that's different. That means you need extreme precision, you need specific precautions to dodge a particular type of problem, or you've got a tiny window of welding settings you have to hit perfectly to get the right properties in the end. It just means higher risk, much tighter control needed.
Right. And what are the main things that decide if it's good or bad? It sounds like it's never just one simple thing.
You're absolutely right. It's always a mix, an interplay. There are really four main factors, and they're all connected. First, the steel's actual chemical composition, what it's made of down at the atomic level. Second, the weld joint configuration, how the pieces are actually designed to fit together. Third, the welding process you choose, MIG, TIG, stick, subarc, they all behave differently. And fourth, the properties you need from the finished weld. What does it actually have to do once it's in service? And look, for those steels with poor weldability, it's just critical. Follow the welding procedure specification, the WPS, to the absolute letter. And you need sharp welding inspectors watching closely. That strict process is your safety net.
Okay, speaking of safety nets, let's dive into some specific nasties we're trying to avoid. The first one, hydrogen-induced cold cracking. That sounds particularly nasty. I've heard it called cold cracking, right, because it happens after cooling. And HAZ cracking, because it's usually in the heat-affected zone.
Yeah, those are common names.
But the one that always gets me is delayed cracking. The idea it can just appear hours, maybe days later, up to 72 hours, you said. That's like a ticking time bomb in the metal.
It really is insidious, that delay. And while, yes, most hydrogen cracks pop up in the heat-affected zone, the HAZ, it's worth knowing they can also form right in the weld metal itself. But for HAZ hydrogen cracking, you need four things happening all at once. It's like a perfect storm. You need hydrogen there above about 15 milliliters per 100 grams of metal. You need significant stress, usually over half the steel's yield strength. The temperature has to be fairly low, below 300 degrees Celsius. And critically, you need a susceptible microstructure in that HAZ. Basically, it has to be hard and brittle, often over 400 HV hardness. The key thing, they all depend on each other. Knock out just one of those four and a crack won't happen.
Wow. It's still hard to picture something so tiny, like hydrogen atoms, causing such huge problems. Can you, walk us through how that works? It's not just pushing things apart, is it?
No, not at all. Think of hydrogen atoms as these incredibly tiny little intruders. They get into the molten weld pool, maybe from moisture in the welding flux or grease, rust, scale breaking down in the heat of the arc. Now, while it's hot and liquid, those tiny atoms can actually diffuse out, escape. But if that weld cools down really fast, especially back to room temperature, those hydrogen atoms get trapped. They can't move easily anymore. And they tend to gather in the heat-affected zone. Now, normally steel in the HAZ might be able to stretch a bit, deform plastically under the stress of cooling and shrinking, but when you've got hydrogen trapped in a susceptible hard microstructure, it makes that steel brittle, like turning rubber into glass. So when the normal tensile stresses pull on it as it cools instead of stretching, bang, it cracks.
Okay, so if you need all four conditions, the big takeaway is stop just one of them and you stop the crack. What are the practical ways? How do you actually do that on, say, a construction site or in a workshop?
Exactly. Prevention is key. Let's start with controlling the hydrogen source. Moisture is the big enemy, usually hiding in welding consumables. So, you bake your stick electrodes properly, keep them in sealed packs, maybe store your submerged arc flux in heated silos. Basic stuff, but vital. You check the hydrogen level certified for your consumables, you use heated quivers or ovens on site for electrodes, keep wire spools covered, even check the dew point of your shielding gas, make sure it's dry. And of course, the joint itself has to be clean. Bone dry, no rust, no scale, no oil or grease.
Okay, that makes sense. Get rid of the hydrogen source. What about the stress? You said stress is needed too.
Right. Managing tensile stress. Look, you'll always have some residual stress from welding, it's just physics. But you can reduce its impact. Good fit-up is crucial. Avoid big gaps or forcing things together. Smooth weld profiles matter. Too sharp changes at the weld toe act like little stress razors. Sometimes you might need a stress relief heat treatment after welding, although that's a whole other process. You can sometimes tweak parameters, maybe increase travel speed to put less total heat in, which means less shrinkage stress overall. Keeping the weld size, the volume of weld metal, as small as feasible also helps. And the stress aspect is particularly important for some of the low alloy steels. They're just much more sensitive.
Okay, hydrogen source, stress, what's the third one? The microstructure.
Yes, avoiding a susceptible HAZ microstructure. A susceptible HAZ is basically one that's become hard and brittle because it cooled too quickly from the welding heat. Think martensite, that hard phase in steel. For typical carbon and carbon manganese steels, if the HAZ hardness gets over about 350 Vickers, 350 HV, alarm bells should ring. Now, how hard it gets depends on two things: the steel's chemistry and how fast it cools. We use a thing called the carbon equivalent value, or CEV, for C and CM steels. It's like a recipe score for hardenability. Carbon has the biggest effect, hence the name, but other elements add to it. Higher CEV means it's more likely to get hard and brittle, and faster cooling rates. Definitely increase hardening. Think welding on thick material or using low heat input, it cools faster. So practically. Buy steel with a guaranteed low CEV if you can. Use moderate welding heat input, not too low, not too high, to control the cooling rate. And the big one, preheat. Applying preheat and maintaining that temperature between weld runs, called the interpass temperature, slows down the cooling dramatically. Now here's a critical point, that CEV calculation. It doesn't really work for low alloy steels. Their HAZ tends to get hard regardless. So controlling hydrogen cracking in those materials is just inherently trickier, often needing more careful preheat and sometimes post-weld heat treatments.
Right, preheat. That leads perfectly into the fourth factor, controlling the temperature.
Exactly. Temperature's huge because it controls how easily hydrogen can move, how fast it diffuses. If the weld stays warm, let's say above 300 degrees C, hydrogen can zip around and escape pretty easily. So applying preheat, usually somewhere between 50 and maybe 250 degrees C, depending on the steel and thickness, is crucial. And maintaining that interpass temperature is just as important during welding. It stops things cooling down too quickly between passes. There's also post-heat. That means keeping the preheat on or maybe bumping it up to around 250 degrees C for a couple hours after you finish welding. The whole point is just to give any trapped hydrogen a final chance to diffuse out. Important note, post-heat is not the same as post-weld heat treatment, or PWHT. PWHT is much hotter, over 600 degrees C, and does different things like relieving stress. Post-heat is purely for hydrogen removal.
That's a really clear breakdown for HAZ cracking. But you mentioned hydrogen can crack the weld metal too. What does that look like? Is it the same fix?
Yeah, it can happen in the weld metal. Often looks like chevron cracks, sort of V-shapes running along the weld, often at about 45 degrees to the main stress. Honestly, the exact mechanism isn't quite as well understood as HAZ cracking, but it's more common in higher strength weld metals or really thick sections. Big welds can trap more hydrogen. The solutions: pretty much the same playbook. Use low hydrogen welding processes and consumables, apply adequate preheat, maintain your interpass temperature, give that hydrogen an escape route.
Okay, let's switch gears completely. A different kind of problem. Solidification cracking. This one gets called hot cracking because it happens while it's literally hot, right? Or central line cracking because it runs down the middle. I've also heard the term hot shortness, which paints a great picture. The metal just isn't strong when it's hot and trying to solidify.
That's a perfect way to think about it. Hot shortness. It's exactly that. The weld metal lacks ductility, lacks stretchiness, right as it's turning from liquid to solid. And yeah, these cracks happen when three things come together. One, a susceptible weld metal composition. Two, unfavorable welding conditions that create a bad bead shape. And three, high restraint or tensile stresses pulling on the weld as it cools.
So how does that actually form the crack? What's the mechanism that creates this, well, hot mess, as you called it?
Okay, imagine the weld pool solidifying. It doesn't just freeze instantly all at once. It usually freezes from the edges inwards, like ice forming on a pond. As the main part solidifies, it pushes any remaining liquid bits, the stuff with lower melting points, towards the very center, the last part to freeze. Think of things like sulfur or copper impurities forming little liquid films. So you end up with this thin film of liquid trapped right down the center line, while the metal on either side is solid and shrinking, pulling apart. That liquid film is incredibly weak. So if the pulling stress is high enough, pop. It just ruptures and you get a crack. Often you can see it right away, a crack running down the middle of the weld bead, sometimes quite wide.
Right, I can picture that weak liquid film tearing. So knowing that, what are the practical things you can do? How do we avoid this hot cracking?
Again, same principle. Break one link in that chain of 3 conditions. First, weld metal composition. Honestly, most modern carbon and CMN steels are pretty good these days. The danger is contamination. Sulfur is a classic bad actor. It forms iron sulfides that stay liquid down to maybe 980 degrees C. Copper is another. It can form films, liquid, around 1100 degrees C. Where do they come from? Sometimes oil or grease left on the joint, sometimes the parent metal itself, if it's maybe an older or less refined grade, dilutes into the weld pool. So rule number 1, clean the joint before welding. Absolutely spotless. Also, check things like copper backing bars or contact tips in your MIG gun. Make sure they're in good shape and not melting into the weld.
Okay, keep it clean. What about the second factor, the welding conditions and the bead shape? Ah, yes, the bead shape. This is fascinating, actually. It comes down to the width to depth ratio of the weld bead. If you have a bead that's deep and narrow, say, the depth is more than twice the width, a ratio greater than 1.2. That's bad news. Why? Because that shape tends to trap that low melting point liquid right in the center, making it prone to cracking. But if you can get a bead that's wider and shallower, maybe the width is more than twice the depth, a ratio less than 1.2. That's much better. That shape tends to push the last bit of liquid towards the surface where it can solidify without being trapped under high stress. It can kind of self-heal. Now, some welding processes are just more likely to give you that deep, narrow shape. Submerged arc welding, spray transfer GMAW or MIG, they penetrate deeply. Even electron beam or laser welding, with their super high energy, can be prone to it.
So how do you adjust? If your process tends to make that risky shape, you tweak your parameters. Generally, reducing the welding current tends to make the bead shallower. Reducing the travel speed tends to make the bead wider. So you play with those. And specifically for crater cracking, that little star crack you sometimes see right at the end of a weld bead, there are techniques like using a current slope-out function on a TIG welder, gradually fading the power. Or you can backtrack slightly at the end of the weld, just weave back over the end of the bead. With stick welding, sometimes just reversing direction for a tiny moment to fill the crater properly works wonders. I remember an old-timer showing me his special wiggle at the end of a run. Turns out he was instinctively doing a perfect little backtrack to fill the crater.
Clever. Okay, next up, lamellar tearing. This one sounds different again. He said it happens under the weld, in the plate itself.
That's right. Lamellar tearing is quite specific. It only occurs in rolled steel plate or sections, and it forms within the parent material, typically just underneath the weld, outside the HAZ. It looks distinctive too. It runs parallel to the plate surface and the weld fusion line, often with a kind of stepped or terraced appearance. And yeah, you see it most often in carbon manganese structural steels.
So what has to happen for this crack to form?
You need 2 things together. First, a susceptible rolled plate. The plate itself has to have poor ductility in one specific direction.
Right.
And second, you need high stresses pulling in the through thickness direction. That's the direction perpendicular to the rolling surface, sometimes called the short transverse direction.
Okay, susceptible plate plus stress pulling through its thickness. What's actually going on inside the steel to cause that stepped crack?
Well, that susceptible plate has low ductility through its thickness because of tiny non-metallic inclusions. Think microscopic bits of dirt, essentially often manganese sulfides or silicates. During the hot rolling process when the steel plate is made, these inclusions get flattened and stretched out into long, thin stringers parallel to the surface. Imagine layers of pastry with weak spots between them. Now put a weld on top. Especially in thick sections or joints like T-joints or corner joints, welding creates high residual stresses that pull perpendicular to those weak layers through the thickness. These stresses cause the weak interfaces around the inclusion stringers to separate, to decohese. Then the thin ligaments of steel between these opened up inclusions just tear, linking them up. That creates the characteristic stepped crack face.
Right, like pulling apart layers. So how can you, the person designing or building something, stop this hidden tearing from happening?
Again, you target one or both of those conditions. First, deal with the susceptible plate. You can actually test for susceptibility using a through-thickness tensile test. You measure how much the area reduces before it breaks when pulled in that direction. If you get over about 20% reduction of area, the steel generally has good resistance, even in tough joints. Practically, this often means specifying clean steel with very low sulfur content, usually below about 0.015% sulfur. Fewer inclusions mean less risk. You can also buy steel certified to specific standards like EN 10164 in Europe, which guarantees certain levels of through-thickness ductility. Z-quality steel, they sometimes call it.
Okay, so use better steel if you can. What if you're stuck with potentially susceptible plate? Can you reduce the stress?
Absolutely. Reducing the through-thickness stress is often about clever joint design. Maybe instead of a full penetration T-joint weld that pulls directly through the plate thickness, you could use balanced double-sided fillet welds, or perhaps partial penetration welds. Another really neat trick is to apply a buttering layer. You basically weld a layer of tough, ductile weld metal onto the surface of the susceptible plate before making the main structural weld. This buttering layer takes the strain. The highest stress then occurs in the ductile weld metal, not in the brittle plate underneath, or in some cases you might redesign the connection entirely. Maybe use a forging or an extrusion as an intermediate piece, so the weld joins onto that, and the susceptible plate doesn't see those direct through thickness pulls. The goal is always the same. Avoid putting high stress through the weakest direction of the plate. Eliminate one condition, eliminate the problem.
Okay, final imperfection for today. Weld decay. This sounds corrosive, and you said it's different because it's not a crack made during welding, but a failure that happens later in service.
Precisely. Weld decay isn't a fabrication flaw. It's a form of corrosion that attacks a very specific zone after the component has been put into use. You see it as a narrow band right in the heat-affected zone alongside the weld that gets severely corroded, while the weld itself and the parent metal further away might look perfectly fine. And crucially, it only affects certain types of austenitic stainless steels.
So what are the conditions needed for this kind of decay?
Just two things need to line up here. One, you need a sensitive HAZ in that stainless steel. The welding has to have made that zone vulnerable. And two, that component needs to come into contact with a corrosive liquid during its service life.
Okay, this raises an important question then. Why does the HAZ become sensitive to corrosion? What happens during welding to make it vulnerable later on?
Good question. It's about chromium carbides. In standard austenitic stainless, steel's the ones without the L for low carbon, like standard 304 or 316, if the HAZ gets heated into a specific temperature window, roughly 600 to 850 degrees Celsius. Something happens at the grain boundaries, the tiny borders between the metal crystals. Chromium atoms and carbon atoms decide to team up and form chromium carbides right along these boundaries. As these carbides form, they suck the chromium out of the metal immediately next to the grain boundary. Now, chromium is what gives stainless steel its stainlessness, its corrosion resistance. So these areas right next to the grain boundaries become depleted in chromium. They lose their protection. Later, when that part is sitting in a corrosive environment, the corrosion preferentially attacks these weakened chromium-depleted grain boundaries. It eats its way along them. And the more weld runs you do, or the thicker the material, the longer the HAZ stays in that dangerous 600 to 850 degree temperature range, making the problem worse. More carbides form.
Okay, so the heat of welding basically sets up these weak pathways for later corrosion. How do we stop the HAZ from becoming sensitive in the first place?
It really comes down to two main strategies: smart material selection and controlling welding parameters. The simplest way is material selection. Just use the low-carbon L grades like 304L or 316L. They have so little carbon that there just isn't enough to form many harmful chromium carbides, even if they get heated into that temperature range. Problem solved, usually. Another option is to use stabilized grades. These have small amounts of other elements added, like titanium in grade 321 or niobium in grade 347. These elements grab onto the carbon even more readily than chromium does, so they form titanium or niobium carbides instead, leaving the chromium in place to protect the steel. Now, if you absolutely have to weld the higher carbon grades, then your only option with welding parameters is to minimize the time spent in that risky temperature zone. That means using low heat input welding procedures and making as few weld runs as possible. Keep it cool, keep it quick. Technically, you can fix a sensitized HAZ after welding with a high temperature heat treatment called solution annealing. welding, around 150, 1100 degrees Celsius. That dissolves the carbides back into the steel. But honestly, doing that on large fabricated items is often impractical or impossible. So the real solution lies in choosing the right material, L grades or stabilized grades, or controlling the welding up front. You can't easily change the corrosive surface environment later, so you prevent the sensitivity from forming.
So what does this all mean? We've covered a lot of ground today.
Mhm.
It's really clear that weldability isn't simple. It's this intricate dance between the steel's chemistry, the physics of heating and cooling, and just really careful, precise work. But by understanding these specific problems, the sneaky hydrogen crack, the hot solidification crack, the hidden lamellar tear, and that corrosive weld decay, by knowing the conditions they need, we can actually make smart choices. Choices that ensure the things we build, the things we rely on, are genuinely safe and reliable. It really changes how you look at welded stuff.
Absolutely. And it circles back to that core idea we talked about. For so many of these potential weld defects, you just need to break one of the conditions needed for them to form, just one. That understanding lifts welding from just sticking metal together to, well, a highly controlled science and art. It's fundamental for making things that last and, crucially, things that are safe. It's about being deliberate, being precise.
It really does make you think, doesn't it? About all the unseen engineering around us. Think about the bridges you drive over, the planes you fly in, maybe even just the chair you're sitting on. How many hidden deep dives like this one into materials and welding and physics were needed to make sure they're strong and safe just for you? What other invisible engineering choices are shaping your world right now, just waiting for your deep dive to uncover them? Well, that's all we have time for today. Thanks for joining us on The Deep Dive.